Okay, so in this video, we will consider example of differentiation with trigonometric functions. So remember from the class notes, with the help of the two key limits, we were able to find that the derivative of sine of x was simply cosine of x, and the derivative of cosine of x was negative sine of x. Suppose we wanted now the derivative of the other trigonometric functions. Well, remember that tan of x is given by sine of x over cos of x. We have secant of x, which we write as SEC, and secant is 1 over cos of x. And then we have the mirror images. With tan of x, we also have cotangent of x. So it's just 1 over tangent. Therefore, if you do 1 over this fraction, you flip the fraction, so you'll have cotangent is cosine of x divided by sine of x. And cosecant of x, which we write as C for cosecant of x. Secant is 1 over cos. Cosecant is 1 over sine of x. So we can now find, say, the derivative of tan of x, and then secant of x, and I will let you find on your own the derivative of cotan and cosecant of x. Right? So let's now find the derivative of tan of x. So if we differentiate tan of x, well, the idea is just rewrite tan of x as sine of x over cos of x. And then we have the quotient of sine of x over cos of x. And we can find the derivative of this expression with the quotient rule, because we know the derivative of sine is cosine, and the derivative of cosine is negative sine of x. So let's see what comes out. By the quotient rule, we have the derivative of the top first. The derivative of sine is cosine of x. So we have cosine of x times the bottom times cos of x minus the function on top, sine of x, times the derivative of the bottom. The derivative of cos of x is negative sine of x. And we divide this by the bottom squared, so cos squared of x. And remember this notation. If you write, let me do it here, if you write cosine and you put the 2 on the cosine, what that means is cosine of x all squared. And be careful not to confuse this with simply cosine of x squared. That is not the same thing. So here we take cosine of x squared. Here we take the square of cos of x. This notation is only to avoid an extra pair of brackets. So now, let's simplify. So what do we have? Cos times cos, that's cos squared. Minus minus will be plus, sine times sine. So plus sine squared of x. And we are dividing by cos squared of x. And if you remember my Pythagoras' theorem, sine squared of x plus cos squared of x for any x is equal to 1. So we have 1 over cos squared of x But we can write this as 1 over cos all squared, because if you square 1, you get 1. And now we can give this a shorter name. 1 over cos of x, this is by definition secant of x. Since we have 1 over cos squared of x, this is secant squared of x. And now we have the derivative for tan of x. We can summarize the derivative of tangent of x is secant squared of x. Just for fun, let's find the derivative of secant of x, and I will let you check the derivative of cotan of x and cosecant of x on your own, and you can check your answer with the summary of differentiation sheet that you will now have. So let's differentiate secant of x, remembering that secant is 1 over cosine. So the derivative of secant of x is, well, the derivative of, and now we replace secant by 1 over cosine of x. Once again, we have a quotient. Let's use the quotient rule. Derivative of the top, which is 0, times cos of x, that's just 0, minus the top, 1, times the derivative of cos of x, which is negative sine of x, divided by the bottom squared, cosine squared of x. Well, we can simplify. We get negative negative, so all we have is sine of x over, and here I'll write cos squared as cosine of x times cos of x. And you might ask, well, why am I writing it like this? Because I'm going to split up these two together, and the 1 over cosine, and then let's see what comes out. I'll write first the 1 over cosine. If you prefer, this is sine of x times 1. So this will be 1 over cos of x times sine of x over cos of x. But both of these now we have shortcut names for them. 1 over cos of x, this is by definition secant of x. And sine of x over cos of x, if you remember, sine of x over cos of x is tangent of x. So sine of x over cos of x, that's tangent of x. So all we have is secant of x times tangent of x. And that is the derivative of secant of x. The derivative of secant of x is the function itself times tangent of x. And as I've said before, I will let you now find the derivative of cotan of x, again using the quotient rule, the derivative of cosecant of x, once again with the quotient rule. And you will arrive at very similar results as in the case of the derivative of tan of x and secant of x. So now, let's use these four derivatives. Derivative of sine is cosine. Derivative of cos is negative sine. Derivative of tan is secant squared. Derivative of secant is secant tangent. And now let's go back to our basic rules of differentiation, and I will include trig functions to see that really nothing changes other than using these new formulas of differentiation for the trigonometric functions. So let's just rewrite them on top. So the derivative of sine of x with respect to x is just cos of x. The derivative of cos of x is negative sine of x. the derivative of tan of x is secant squared of x. And finally, I'll write it underneath, the derivative of secant of x is secant of x times tangent of x. Let's do an example first with, say, the product rule. What if we asked for the derivative now? So we'll leave this up here. Of, say, sine of x times cos of x. We have a product, so we use the product rule. So the first function is sine of x times the second function cos of x. The product rule says the first term is the derivative of the first function, and the derivative of sine is cosine of x, so we'll get cos of x times the second function, cos of x, plus, and now we differentiate the other function, so plus the first function, sine of x, times now the derivative of cos of x, which we know to be negative of sine of x. So finally, cos of x times cos of x is just cos squared of x. Sine of x times negative sine of x will give us negative sine squared of x. And that's the derivative of sine of x cos of x. What if we have, say, two products? What if we looked for the derivative, say, of x squared times sine of x times, just for fun, tan of x. Now we have two products. It is x squared times sine squared times tangent of x. So we have to use the extended product rule, which says first, derivative of the first function, so 2x, times everything else. Sine of x, tan of x, plus the derivative of the second function, which is cos of x, times everything else, therefore x squared tan of x, and finally plus the derivative of the third function, derivative of tan of x is secant squared of x, times everything else, x squared sine of x. And that's a derivative of x squared times sine of x times tangent of x using the extended product rule. If you wanted, and then this is just algebra, you could look for common terms. This is multiplied by x, x squared, and x. So there is a common factor of x that you could factor from the expression. And you could simplify a little bit more. For example, tangent is sine over cosine times a cosine, so this would just be x squared times sine of x. Here you can't really multiply because tan is sine over cosine, so we'd have sine squared over cos. Not much better. And same thing here, this is 1 over cos squared times sine, no cancellation. So the only cancellation you could really do here, other than factoring the x from each term, is to write cos times tangent as just sine of x. Let's consider now an example involving the chain rule. So what if we said the derivative, and you'll see where we have to be careful, say, of sine of x squared. Now we said here of, so we have a composition. This is sine of x squared. So think of it this way. If I give you a value of x, and I ask to evaluate sine of x squared, well, you would first square x, then compute the sine of this value. So the outside function is sine. So the chain rule says differentiate the outside function. The derivative of sine, if you remember, is cosine. So we'll have here the derivative of sine is cosine. We differentiate sine, cross it off, it's gone. Cosine of what? Of whatever is left over, which is x squared. But there is something left over that we have not differentiated, and that is the x squared term. So the chain rule says we have to multiply whatever we have thus far by the derivative of the leftover function. The derivative of x squared is just 2x. We differentiate, we cross off. Nothing's left over, so the derivative of sine of x squared is 2x cos of x squared. And because usually we write, when we have a product of several terms, we write the simplest terms first, and then later the more complicated one. So 2x cos of x squared. Now what if we ask for the derivative of now sine squared of x? Well, remind yourself that here we're squaring the sine function. So now rewrite this. This is the square of sine of x. So now the outside function is no longer the sine, but the power 2. So if I give you a value of x, and I say evaluate this expression, you will first plug it in, then take sine of x, and then finally you will square it. So the power 2 is the outside function. So the chain rule says we must differentiate the outside function. We have a power 2, so we use, of course, the power rule. We bring the exponent down. Subtract 1 from the exponent. 2 minus 1 is 1. Differentiate, cross off, and you're left with 2 times something to the 1th power of whatever is left over, which is sine of x. But there is something left over that we have not differentiated, and that is sine of x. So we have to apply the chain rule again, which says we multiply what we have so far by the derivative of what's left over. What's left over is sine of x, and the derivative of sine of x is cosine of x. So, if we drop the silly power 1, the derivative of sine squared of x is actually 2 sine of x cosine of x. Let's do a couple more examples. Let's do one with, say, secant. Let's just differentiate secant of something. And let's take, say, 5x plus 1. Once again, here we have a composition, right? If you read this out loud, this is secant of 5x plus 1. We have a composition. So if I give you a value of x and I said to evaluate this expression, you would first do 5 times x, then you would add plus 1, and then you would find secant of this expression. So the outside function is secant, and the derivative of secant is secant times tangent. So the derivative of secant is secant times tangent. That's the derivative of secant, secant tangent, cross it off, of what? What is the argument of both of these functions? The argument is whatever is left over. 5x plus 1, 5x plus 1. But there is something left over that we have not differentiated, and that is the 5x plus 1. So the chain rule says we must multiply what we have so far by the derivative of what's left over. Well, what's left over is 5x plus 1. The derivative of this is quite simply 5. Differentiate, cross off, and we're left with nothing. So we're done with the derivative. As always, write the simplest terms first. So this will just be 5 times secant of 5x plus 1 times tangent of 5x plus 1. And there you go. So you see, as far as the derivatives involving trigonometric functions, nothing changes. You still apply the product rule in the same way, the chain rule in the same way. The only difference is you have a few new formulas for the derivative of the trigonometric functions. If you had, say, a quotient, same thing, you would use the quotient rule. Now, one last mention, and that is before you differentiate a function involving trigonometric functions, always ask yourself if you can simplify beforehand. So what if I asked you to find the derivative, say, of let's go with cosine cubed times tangent of x. Now here, if you think about it, well, you could use the product rule, but if you remember, tan is sine over cosine, so you'll be able to cancel a cosine here and have a slightly simpler rule of differentiation. So you can write this as the derivative of cosine cubed of x times sine of x over cos of x. And now, cos cubed over cos gives you cos squared. So that would give you the derivative of cosine squared times sine of x. We have a product, cos squared times sine of x, so we must use the product rule. The first function is cosine squared of x. The second is sine of x. Let's differentiate. By the product rule, what we need first is the derivative of the first function. And be careful here. To differentiate cos squared of x, we have to use the chain rule. This is cos of x all squared. Differentiate the outside function first, the power 2 function. Bring 2 down. Subtract from the exponent. 2 minus 1 is 1. Of what? Of cos of x. But that's just the derivative of the power 2. So complete the chain rule times the derivative of cos of x, which is negative sine of x. And that's just the derivative of the first function, cos squared of x. We have to multiply this by the second function, which is sine of x, plus now the first function, cos squared of x, times the derivative of the second function. Derivative of sine of x is cos of x. And now we can simplify. So what do we have? Well, negative sine times sine is negative sine squared. We'll pull the negative up front, and we'll have negative 2 cos of x sine squared of x. That takes care of this term, plus cos squared times cos of x leaves you with a cosine cubed of x. And if you want here, well, you can factor a cos of x from both expressions. That's not much, but it's something. And you would have cos of x times. Well, if you pull cos of x from this term, you're left with negative 2 sine of x squared. Sorry, not sine of x squared. Sine squared of x. Plus, if you factor cos of x from cos cubed, that leaves you with cosine squared of x. And there you have it. So always remind yourself that whenever you differentiate trigonometric functions, everything is the same with the product rule, the power rule, the quotient rule, the chain rule, except we have just a few rules of differentiation. So formulas for the derivative of sine, cosine, tangent, and secant. And on your own, remember to derive the formula for cotangent, cosecant. So go out there, find some derivatives, and have fun.